Hey everybody, it's Mrs. Harbin. We're doing video notes 8.2. So now we're going to start putting the numbers together with what we know about heat and temperature changes and how that transfers, okay? So we're going to do some definitions and let's get busy, okay? The fact that you can ice skate on ice has a lot to do with phase changes and pressure, and so that's why that hockey guy's on there, okay? Read chapter 10 and chapter 14. All right, so heating curves. All right, it's your main heating curve. And in that main heating curve, there's slanty parts like this, and there are flat parts like that. Okay, slanty parts involve a temperature change, and the flat parts involve a phase change. Okay, phase change. So we're going to have to calculate the heat involved in all of those. All right, so a slanty part is on your graph this way. What's happening on a slanty part? A temperature change. The equation is Q equals mc delta T. So what do you need to know? You need to know M for the mass. You need to know C is the specific heat of that substance. Okay. And you need to know the change in temperature that it goes through. Change in temp. In order to calculate the heat. Right? So you need to know all of that to do it. So if you had 223 joules of heat, so that's your Q, to 19 grams of water, that's your mass. Here's your C, specific heat. How much will the temperature change? So you're finding delta T. So yeah, Q equals mc delta T. We're looking for delta T, so we need to know Q, M, and C. How did I do that? I brought the M and C over. So the change in temperature is going to be equal to the 223 joules divided by the 19.0 grams of the substance divided by the specific heat of the substance in joules per gram degree Celsius. Joules cancel joules, grams cancel grams. 1 over 1 over Celsius equals Celsius. So the change in temperature is 2.81 degrees Celsius. There's your delta T. Okay, so a slanty part uses the MCAT equation. Make sure you use the specific heat of that substance. So what does the specific heat mean? Okay, amount of energy to change 1 gram of a substance, 1 gram of substance by 1 degree Celsius, by 1 degree Celsius. Okay, so if you're changing, so heat is calories, 1 gram of a substance, 1 degree Celsius. Here are the units: calories per gram degree Celsius, or joules could be heat per gram per degree Celsius. Okay, specific heat is now evening out all of the substances we know to figure out how much it takes to change each substance's temperature, how much heat to change the temperature of 1 gram of a substance. So specific heat is for changing the temperature of a substance. Each substance has a different specific heat. High C equals slow temp change. Okay. Low C equals fast temp change. Okay. All right, so changing temperature means you're changing the kinetic energy of a substance. Kinetic energy is energy of motion. Temperature is average kinetic energy. Again, here's the formula. Big Q, little q doesn't matter. M mass, C specific heat, delta T is temperature change. Change in temp. Okay, make sure you memorize this, the units and what it means. Okay, now that was for all slanty parts. Now we're talking flat parts. Flat line phase change. Flat line phase change. So, can we use the temperature change equation? No, because there's no delta T. So we have to use a different equation. That equation is Q equals M delta H. Big Q, little q doesn't matter. M is mass, and delta H is the heat change for the amount of heat it takes to change 1 gram of a substance into a new phase. All right? So Q is heat, calories are joules. M is mass in grams. Delta H is the heat of the phase change in calories per gram or joules per gram. So let's look at the next slide like it says. All right. Heat of fusion is called delta H. Fusion is melting. So for us, heat of fusion is the change, the heat it takes to melt 1 gram of a substance. Okay. It's if you were melting it, it's fusion. If you're freezing it, it's all right. So delta H of is fusing or freezing, it's the same amount of energy. The difference is if it's melting, the heat's going in. If it's freezing, the heat's going out. Okay, calories per gram are the units. If you want to use kilocalories and moles, calories and moles, you can change these grams to moles. We know how to do that. So if this is for solid to liquid or liquid to solid phase change. Okay, so if we want to find delta H, we need the mass in grams and the heat in joules, and we want to know the delta H. So Q equals M delta H. Plug in the Q for 166.3 joules. Plug in the mass, 10 grams. What is the delta H? That's what we're trying to find. So we got to take the 166.3 joules divided by the 10 grams, and we get 16.63 joules per gram. So if you want to freeze that shampoo or melt that shampoo, you need to put 16.63 joules into every gram to make it melt. Okay, what's the difference between that and this? This is vaporization or condensation. This is the liquid to gas phase change, and this is the gas to liquid phase change. Either way, it's the top flat line on a heating curve. All right, so if something's boiling or condensing, this is the same amount of heat, whether it's added in or taken away. Calories per gram, joules per gram, kilocalories per mole. Here's the formula. Okay, so find the delta H vape. Okay, find that given grams, so there's our mass, and given joules, so there's our Q. So we need to put in the 279 joules for every 9.33 grams, and we need to know our delta H. So we do 279 joules divided by the 9.33 grams, and we find out that it will take 29.90 joules to vaporize every gram of that shampoo. Okay, and shampoo makes you look really good, says the horse and the lady. Okay, so what if we need to do a lot more than just vaporize or freeze or change the temperature? Let's see, we got a graph going on here. We're starting at -6 degrees Celsius, we're ending at 116 degrees Celsius, and we're talking about H2O. All right, so let's draw a graph for it. Well, ice has significant changes at 0 degrees Celsius and 100 degrees Celsius. I have to put those on there because they're in our temperature range. So we're going to start there, we're going to melt, then we're going to heat it up, temperature change till it boils, and temperature change again. So we have 5 sections of a graph. Over here it's solid, here it's solid turning to liquid, here it's liquid turning to gas, here it's all gas. So guess what we got to do? We got to calculate Q for each section of this graph. So we have to do the Q for the solid is going to be the mass of the solid times the temperature change of the solid, 6 degrees Celsius, times specific heat of the solid is 0.50 calories per gram degree Celsius. All right, and then we're going to have to add to it how much heat it takes to change from solid to liquid. So we need the mass of the solid, the mass of the substance times the heat, the phase change, calorie per gram. Okay, but we're not done because that just takes care of the heat for those 2 sections. We need the heat for that section. Q total. All right, so this is the Q for just the solid. This is the Q for the solid turning to the liquid. Now we need to add to that the heat it takes to change the temperature of that liquid 100 degrees Celsius. And the specific heat is calories per gram degree Celsius. Okay, so this is the Q for changing the liquid by temperature. All right, but then we got to change the liquid into a gas. So we need the mass of the substance times the heat it takes to change the liquid to the gas, calories per gram. But we're not done because once it's all gas, we need a Q for that. So we'll take the mass of the solid times the temperature change. I said solid, I meant gas. 16 degrees it changes temperature when it's a gas, and the specific heat of that steam is 0.50 calories per gram degree Celsius. So what I do is I get answer for all that, and I get so basically the first one is 12.5, and notice the units are calories. All right, plus 400, and the units for that are also calories, plus 500 units for that are calories, plus 5 times 540 is 2,700 calories for the fourth Q, plus there's one more Q here, and that is 40 calories. And so the total amount of heat, Q total, is 3,652.5 calories to do this whole process, the whole process. And that's it. Okay, so another problem you might have is heat of vaporization of acetone is 7.25 kilocalories per mole. So how much energy is released if 75.2 grams of acetone is condensing at its boiling point? Energy released, okay, gas turning to liquid is exothermic, so it releases energy, so that means delta H is negative, okay. At its boiling point means it's a flat line. So Q equals M delta H for this, okay. The mass is 75.2 grams, but the delta H we're using is in kilocalories per mole, so I have to change that to moles. It's C3H6O, so that gives me 58.09, thank you, periodic table, grams of C3H6O for every 1 mole of C3H6O. Alright, that takes care of the M, and then the delta H is 7.25 kilocalories per mole. Okay, so what happens? Grams cancel grams, mole from this cancels mole from this. So the amount of heat it takes is 9.35 kilocalories. Okay, so now it's just figuring out which heat equation to use and which units. Okay, so what kind of data do you need? These are our C's for solids, liquids, and gases. Okay, so those are for the MCATs. These are our delta H's. All right, so this is the liquid to solid one, liquid to solid, solid to liquid. And this has to do with gas to liquid or liquid to gas. So these are our delta H's. So you have to be able to use those, and you have to know when it melts and boils so that you can use those as well. Okay. Last but not least, calorimetry is the technique we use to detect heat transfer. Okay. So if you take a hot piece of metal and add it to cold water, what's going to happen? The water gets warmer and the metal gets cooler. Okay. So why does the water get warmer? Because the metal gives it heat. Why does the metal get cooler? Because it gives its heat to the water. Okay, so the key to calorimetry is heat lost. Remember this, heat lost equals heat gained. Don't forget it. Heat lost equals heat gained. Say it, heat lost equals heat gained. So if we know how much heat the water gives off, we know how much we know how much heat the water gains, we know how much heat the metal lost. Okay, remember, heat lost equals heat gained. So the temperature of the water goes up, the temperature of the metal goes down, so we just have to apply this. So here's some data. Water, metal, all right, what is missing? Well, we need to find the specific heat of the metal. So we can so Q of the water and the Q of the metal. So we have an MC delta T for water, and then we have an MC delta T for the metal. The mass of the water is 37.5 grams. Specific heat of the water is 1 calorie per gram degree Celsius. The temperature change of the water is 4.0 degrees Celsius. The mass of the metal is 86.2 grams. Specific heat of the metal is what we're looking for. And the temperature change of the metal is 74.8 degrees Celsius. 74.8 degrees Celsius. So the only thing we're missing is this C. So we can divide everything by 86.2 grams and 74.8 degrees Celsius. Okay, so what happens is grams cancel grams, and those grams, sorry, these grams stay. Grams cancel grams there, or over there. Either way, one of the grams cancels. One of the Celsius cancels, and we're left with calories per gram degrees Celsius. So if you multiply that, divide by that, you get 0.023 calories per gram degree Celsius. What does this represent? It represents the specific heat of this metal. Okay, So calorimetry helps us determine heat change by determining temperature change, and make sure you know Q lost, the heat lost by one thing, is going to be equal to the heat gained by another. And so as long as we know if it's just temperature changes going on, we can figure that out. Okay, I know this is a lot, but the heat is on. Make sure you can draw a heating curve. Make sure you know temperature is constant during phase change flat lines. Evaporation is not boiling, specific heats. All right. Calorimetry is the measure of heat change. Know your fusion from your vapes. Math is fun, you betcha. Okay. The heating curves tell us which equations to use. And then steam burns release more heat because there's extra energy in a phase change. All right. Just remember, you should be able to do all these things when you're doing chemistry for this section of our learning.